Welcome to this tutorial. In this video, we're going to break down a complete vector-controlled drive for a permanent magnet synchronous motor built in Simulink. If you look at the screen, what you see isn't just a random collection of blocks. It's the standard architecture used in nearly every modern high-performance electric vehicle, industrial robot, and CNC spindle drive. The goal of this system is simple. We want the motor to spin at exactly 700 radians per second, no matter what mechanical load is suddenly attached to its shaft. To do that, we use a cascade control structure, an outer speed loop, and an inner current loop. Let's walk through it, block by block, from left to right. Let's start on the far left. We have our speed reference, a constant value of 700. This is the desired mechanical speed in radians per second. Just below it, the actual mechanical rotor speed, labeled omega m, is fed back and compared against that reference. The error between the two enters the PI controller. This is the brain of the operation. When the motor is running too slowly, the PI controller outputs a large Q-axis current command. When it's running too fast, that command drops. The output is called IQ-ref, the Q-axis current reference. Notice that the D-axis reference, ID-ref, is hardwired to 0. This is the hallmark of field-oriented control for a round rotor PMSM. By keeping the D-axis current at 0, we guarantee that every single ampere of stator current goes toward producing torque, with none wasted on flux. There's no flux weakening here. We're operating below base speed, at maximum torque per ampere. Separately, you'll also notice a gain block of 4 sitting near the rotor speed output. That block isn't part of the feedback loop. It simply converts the mechanical speed, omega m, into the electrical speed, omega e, for display on one of the scopes. Since this motor has 4 pole pairs, electrical speed always equals 4 times mechanical speed. Now we hit the subsystem labeled DQ2ABC. This is where the magic of vector control happens. In the physical world, the motor has 3 stationary windings, phase A, phase B, and phase C. But in the control world, we think in terms of a rotating DQ reference frame attached to the rotor magnet. The PI controller gave us commands in that rotating world, IQ-ref, ID-ref, and a zero sequence component, IO-ref. This block performs the inverse Park transformation. It takes the rotor electrical angle, labeled theta E, and uses it to project our 2 rotating axis commands back into 3 sinusoidal stationary currents. If we zoom into the subsystem, you'll see 3 math function blocks. For phase A, the formula is ID-ref times cosine of theta E plus IQ-ref times sine of theta E plus IO-ref. That's the standard inverse Park transform. For phases B and C, the same formula is used, but the angle is shifted by minus and plus 120 degrees, 2 pi over 3 radians. The output is called IABCER, the 3-phase current references that the motor should ideally draw. Next, we have the PWM inverter. But look carefully. This isn't the typical sinusoidal PWM you may have seen in introductory courses. This is a hysteresis current controller. Let's open the compare block, labeled comparative. Here's how one phase works. The actual phase current, say IA, passes through a tiny first-order filter with a time constant of 5 microseconds. That just cleans up measurement noise. Then we subtract the actual current from the reference current, IAR. The resulting error enters a relay block, a hysteresis comparator. If the current error exceeds positive 0.05 amperes, the inverter leg switches on and applies positive 155 volts to that phase. If the error drops below negative 0.05 amperes, the inverter switches off and applies negative 155 volts. So the phase voltage bangs back and forth between plus and minus 155 volts, constantly forcing the actual current to stay within a narrow band around its reference. That band is only 0.1 amperes wide, extremely tight current tracking. The advantage of hysteresis control is that it's incredibly simple, robust, and has an almost instantaneous transient response. The trade-off is that the switching frequency isn't fixed. It varies with the load and operating point, which can make electromagnetic interference harder to filter. The outputs of the three comparators are the phase voltages, VA, VB, and VC, which are wired directly to the motor terminals. Now we arrive at the heart of the model, the permanent magnet synchronous machine block. Let's go through the parameters, because these numbers tell a story. The stator resistance is 2.875 ohms. That's relatively high for a small motor, so we should expect some copper losses and a voltage drop under load. The armature inductance is 1.53 millihenries. Because this is a round rotor machine, the D-axis and Q-axis inductances are equal. There's no reluctance torque to exploit. The permanent magnet flux linkage is 0.175 Webers. That's a strong magnet, meaning the motor will produce a healthy back EMF as it spins. The mechanical parameters are crucial. The inertia is 0.8 times 10 to the minus 3 kg squared, very low. With low inertia, the motor can accelerate quickly, but it's also more sensitive to torque disturbances. Viscous damping and static friction are both set to 0 in this idealized model. There are 4 pole pairs. Remember, more pole pairs means higher electrical frequency for the same mechanical speed, but also higher torque density. From these numbers, we can also calculate the torque constant, 3/2 times the pole pairs times the flux linkage. That works out to 3/2 times 4 times 0.175, which equals 1.05 newton meters per ampere. So for every 1 ampere of Q-axis current, this motor produces just over 1 newton meter of torque. Finally, all initial conditions are 0. The motor starts from a standstill with 0 speed, 0 angle, and 0 current. Before we run the simulation, look at the mechanical input port, labeled TM. This is the load torque applied to the shaft, and it's driven by a step block. From time 0 until 0.04 seconds, the load torque is 3 newton meters, a fairly heavy load for a motor this size. Then, at exactly 0.04 seconds, the load suddenly drops to 1 newton meter. This is a classic disturbance rejection test. We're asking, can the speed controller hold the speed at 700 radians per second when the mechanical load suddenly changes? If the PI controller is tuned well, we should see a brief transient, followed by a rapid correction, with the electromagnetic torque settling to match the new load torque of 1 newton meter. On the right side of the model, we have several scopes. First, ISABC, the 3-phase stator currents. Before 0.04 seconds, under the heavier load, these currents will have a larger amplitude because the motor needs more torque. After the load drops, the current amplitude should decrease. Second, omega E, the electrical speed. Since this equals pole pairs times mechanical speed, it should settle around 2,800 radians per second once the mechanical speed reaches 700. Third, TE, the electromagnetic torque developed by the motor. This should track the load torque, but with much faster dynamics, and you'll likely see high-frequency ripple riding on top of it. That's the price we pay for hysteresis switching. And finally, VBC, the line-to-line voltage between phases B and C. This will look like a chaotic, high-frequency switched waveform. Definitely not a clean sine wave. That's exactly what we expect from a hysteresis inverter. Now let's run the simulation and interpret the results. We're simulating for 60 milliseconds, long enough to capture 2 distinct events, the motor starting from standstill and the load disturbance at 40 milliseconds. Let's begin with the top scope, electromagnetic torque. At time 0, the motor is at rest, but the speed reference is already commanding 700 radians per second. The PI controller responds with a large burst of torque to accelerate the rotor. You can see a sharp spike during the first few milliseconds, briefly exceeding 15 newton meters as the controller saturates. By around 10 milliseconds, the torque settles to a steady average of approximately 3 newton meters. That makes sense. In steady state, the electromagnetic torque must exactly balance the mechanical load torque, which is 3 newton meters during this interval. Look closely at the waveform, though it isn't perfectly flat. There's a ripple of about 0.5 newton meters sitting on top of the steady value. That's the signature of our hysteresis current controller. Because the inverter is bang-bang switching within that narrow current band, the torque inherits the switching noise. At exactly 0.04 seconds, the load drops from 3 to 1 Nm. The torque dips briefly, then recovers and settles to approximately 1 Nm within about 5 milliseconds. That confirms our vector control loop successfully rejected the disturbance. The middle scope shows the electrical rotor speed, omega e, starting from 0. The speed rises quickly, since the motor is producing high torque against very low inertia. It reaches a small overshoot of about 2% before settling at approximately 2,800 radians per second. That's 4 pole pairs times a mechanical speed of 700 radians per second. The flat, steady line confirms that the PI controller eliminates steady-state speed error. At 0.04 seconds, when the load steps down, you might expect the speed to jump, since the motor is suddenly producing more torque than the load requires. But the speed trace stays remarkably flat. The disturbance is barely visible. The PI controller reacts so quickly that the speed never deviates significantly. That's exactly the behavior you want in a high-performance servo drive. Finally, the bottom scope shows the three-phase stator currents, I, S, A, B, C. During the startup interval, the currents are large and somewhat distorted, peaking around 30 amperes, as the controller pushes maximum current into the windings to generate that initial torque burst. Once the speed locks onto the reference, the currents settle into clean, balanced three-phase sine waves, the hallmark of successful field-oriented control, oscillating at about 446 Hz, which matches our electrical speed. Before 0.04 seconds, under the 3 Nm load, the current peaks at around 5 amperes. After the load drops to 1 Nm, the peak amplitude falls to around 1.7 amperes, roughly a third as much. That makes sense, because with ID held at 0, torque is directly proportional to Q-axis current, so less torque simply requires less current. You can also see fine high-frequency ripple riding on the sine waves. That's the hysteresis controller keeping the actual current inside its narrow band around the reference. So, as a student, I encourage you to run this simulation, then try changing the PI gains. If you make them too aggressive, the current references will saturate and the system will oscillate. If they are too slow, the speed will dip noticeably when the load steps. That is how you learn. That concludes our walkthrough of this PMSM vector control Simulink model. If you have questions about tuning the PI controller, or if you'd like to see how to replace the hysteresis inverter with a space vector PWM version, let me know in the comments. Thanks for watching, and good luck with your simulations.